Okay, I think we'll get started. We have a lot that we want to cover with you today, and we're really excited to be here. So let's get started. If there are any last takers, so yeah, there's only one screen, so the further you sit this way, probably the easier it will be able to see. We have shared the link to the slides. It's a bit.ly link, and then just fact-slides, and you can then view all of the slides that we will be covering, and in the slides are also the links to the collaborative coding notebooks that we'll be using. So if you are sitting further away, that might help you to see what's happening. And if there are any last takers who want to use the QR code that's on the screen or the link that's underneath it, we wanted to start by just getting a sense of who's in the room, what you're thinking about, what kind of research questions you're thinking about, and what's bringing you to the session today. So I'll just give you one moment in case anyone wants to. You can use your phone or your laptop to tell us a little bit about yourself. And again, the slides are at bit.ly fact-slides. Okay, so I'll start just by introducing us. I'm Maria Antoniak. I'm a postdoc at the Allen Institute for AI. I work on model instabilities, measuring things like values and narratives, and natural language processing for healthcare. Also here today is David Mimno, a professor at Cornell University who studies methodologies to help people learn about culture through documents. Melanie Walsh, who's a professor at the University of Washington, who studies digital humanities, language use on social media, and accessible tools and data. Not here today, but who is also involved in this tutorial project is Matthew Wilkins, who's a professor at Cornell University, and who studies modeling literature and AI for underserved communities. And then Luca Soldani, my colleague at the Allen Institute for AI, who studies information retrieval, building NLP tools and systems for open science. And now let's see a little bit about all of you. So I'll just read aloud some of the answers so we kind of all get a sense of who's here in the room and what's bringing you here. So I'm working on counterfactual explanations for black box models. How can we audit a large language model? My research revolves around bias identification in large language models and centrally looking at nationality biases. Understanding how they work will help me understand how to work on bias mitigation. Data scientist in a company. And yeah, a lot of interests recently in large language models and their uses, but also many concerns. Working on questions of fairness in machine learning driven by personalization, how to make large language models responsible, how to regulate large language models, how large companies like OpenAI can moderate content, mitigating unanticipated risks, and balancing privacy and security, social implications of large language models, validating assessments that use large language models, applications in different contexts, working on data protection and targeted advertising, how LLMs might help us understand the non-human, again, how to audit them, working on sequential behavior and physiological data, especially for health or for example, for health and wellness applications, and demystifying LLMs. What do LLMs mean for communication of thought? How to explain the impacts of them? And a late-breaking answer, how to translate academic recommendations and best practices to industry. Super interesting. We love that you're all here, and we're excited to learn with you all for the next 90 minutes. So our goals today are descriptive. We want you to learn about how large language models, or LLMs, work under the hood and how to access their internals and run experiments with them via code. We want you to come away feeling empowered to test these models, critique them, and use them in ways that are valuable for you. And this tutorial is aimed at beginners. So those who maybe haven't written a lot of code before or haven't done as much machine learning before, but everyone's welcome to be here with us in the room. These large language models, like ChatGPT is one you might have heard of, have overwhelmed the field of NLP. And some questions that we think broadly you might be bringing as fact researchers are, how can you probe those models to measure their biases and fairness issues? And how can you use these models to explore biases and fairness issues in other data sets of interest? And just because more people have come into the room, I'm just going to quickly flip back to the first slide and say that the slides are available at bit.ly/fact-slides. So it's a bit.ly link and then fact-slides, because I know it's hard to see from that far corner. And yeah, so how can you use these models to explore biases and fairness issues in other data sets of interest? So not just in this pre-trained model itself, but in a data set that you might be working with. This tutorial is part of a larger project called AI for Humanists that grew out of a previous tutorial project called the BERT for Humanists project that Melanie Walsh, David Mimno, and Matthew Wilkins and I have all been involved in. What do you need for this tutorial? You don't need anything. You don't need any special equipment. You don't need to set anything up. You don't need to know anything about deep learning. Everyone's welcome to be here and hang out with us. If you have a laptop and you would like to follow along in the slides or later in the code, that might be helpful, but you can also just lean back and take it all in. A flexible schedule, roughly what we're going to be doing. We're going to start with a demo where we're going to try out one of these language models together as users. Then we'll have some lecture, then an interactive coding notebook that we'll go through together. We'll take a short break, and then we'll again have some slides or lecture, and then a final notebook. And to give a sense of where we're going before we drop into the details, we're going towards large language models, and what are they? So given a text prompt, these models can generate a continuation one word at a time, and that can manifest in different ways and for different use cases. So there's things like ChatGPT, where we prompt with a question and it will continue with an answer. There are also applications like machine translation, so we prompt with English and we would like the model to continue in Italian. And then also text and documents, so prompt with a current text and continue with the next 1 to 2 next words. So let's try this out together. Some people may have already used chatbots and large language models extensively, others may not. We'd like you to try it out. We've put just a little demo together around around GPT 3.5 so that you can easily try out some of these questions and examine the responses. And we'd like to take about 5 minutes right now for you to visit this link, so fact-demo.allen.ai. And if you're comfortable, try out the demo. We've seeded the demo with some questions. I'll switch to the demo tab now, but again, the link is fact-demo.allen.ai. So this exercise will allow you to interact with a chatbot from OpenAI. We'd like you to think of concrete scenarios in which these models are being used or could be used, ask questions related to those scenarios, critically examine the responses, and discuss with your neighbors what you observe. And a note, so whenever you use GPT models, your questions are being recorded by OpenAI. Just keep that in mind. Don't put any private information in there or anything that you don't want them to have a record of. And this is optional, you don't have to do this part, but we think it might be interesting to try this out and discuss. We are not collecting any of that data. We're not collecting it, and we wouldn't use it for anything if we did, but we're not collecting it. We've seeded this with an example high-stakes scenario of healthcare workers or pregnant people using a chatbot to answer questions related to maternal health. So we put in some example questions. You could try out these exact questions if you want. And you can ask multiple questions. Just edit your question and click submit to generate a new response. Again, don't include any private information like real names or dates. So I can put in a question here. Click submit, and it will generate a response for you. We'd like you to think creatively. Again, we've given this example of this high-stakes healthcare scenario to ground your brainstorming and question asking, but you could ask questions about something else as well. So take a few minutes to try this out, and we'd like you to, with the people next to you, maybe work together and talk about the responses that you're seeing, problems that you see with them, the constraints on the types of responses, who might be using it, whether they should be using it, etc. So we'll take a few minutes now to do this. And I'm just going to tab back over to the link so people can see it. It sounds like we may have crashed our demo. Can people access the URL, or it's when you try and ask a question that it... Both. Okay. Well, can't troubleshoot it now. That's too bad. If anyone was able to use the demo before it crashed and would like to share any thoughts, we'd love to hear. I don't know if anyone was able to ask some questions. Yeah, there's a microphone set up there, or yeah. Just your observations or opinions on the responses you saw. Yeah, keep trying. Maybe it will come back up.
Okay, so we started with some easy questions like how can you decrease morning sickness? And most of the things it said were kind of valid, like keep some crackers, have smaller meals. What struck me a little bit was it suggested taking B6 supplements. It's not medication, but I'm not so sure it's like entitled to suggest anything like that. So.
Thanks. I asked how it was trained, and it didn't seem to give any answer indicating that it was a model itself. It didn't. It just gave an answer in abstract. Machine learning models are trained by such and such a process. So I couldn't actually interrogate the model itself.
Oh, I tried asking a question around, like scheduling for shifts that, if all these people didn't want to work, but 2 people did, how would you schedule it? But the answer didn't really make sense.
So I asked what the best methods would be to save as much CO2 as possible. And what I found interesting is that the answers are all very focused on what we as individual people can do, basically, which is nice, but it's also just, part of the picture, right? There are other very big steps that would make a big impact that is not just the individual person. So I thought it would be nice to see a little bit more, like a more holistic answer.
I asked what the best vitamins to take are when you're pregnant, and I noticed that it started off kind of with like a hedge of like, it's important to talk to your doctor, and then it was like, however, here's some advice. And the advice just kind of named specific things, so maybe in some sense that's good because you're not recommending specific dosages, but on the other hand, right, that could also be a con.
Yeah, these are great observations. I'm gonna not interpret what you've been telling me, but just kind of leave the question open of what it's like to use these models, how they should be used. I'll leave the demo. The demo will be up the rest of the session if you want to keep trying things. Oh, sorry, was there one final?
Yes, we wanted to be a bit controversial, so we asked how to terminate a pregnancy, and we got a quite interesting reply. That is, as an AI language model, I cannot provide biased information or promote unethical practices. And I think, it's quite striking that the first sentence is this. It proceeds saying that, okay, consult a professional that can advise you. But still, this first sentence is a bit, I don't know, weird, let's say. Thanks.
I guess all I would say, probably to just close this little demo part, is that this is exactly where your different domain expertise can really come in, and what types of questions you might ask the model and how you interpret those outputs. This is something where, yeah, your domain expertise can be extremely helpful. So now that we've all, or mostly all, had a chance to try this out ourselves, let's dig in. What is happening? What's inside this model? How does it work? Starting at the low level. So computers don't understand words, but they do understand numbers. So how can we turn words into numbers? This is the question of the day. And in natural language processing, there's a famous hypothesis that says you shall know a word by the company it keeps. This is called the distributional hypothesis. And what that means is, what it's kind of asking is which words often appear together. And how we use this hypothesis is that we can learn about the meaning or the usage of we can learn about the meaning of a word by studying its usage, or the usage as a proxy for the meaning. And we can also use that proxy, the usage, to study a word's semantic relationships with other words. And the goal here is to represent semantic similarity with numbers. That's a broad goal of a lot of natural language processing and also underlying these models. So imagine representing every possible idea with a number, like the Dewey Decimal System. Like maybe someday in the future, far future, that would be possible. But such a system is inflexible and can't represent facets of meaning. So what if we represent a word or a concept with multiple numbers? So a definition of two words that we'll be using a lot: vector and matrix. So vector is a list of numbers, and a matrix is a list of lists, a two-dimensional list of numbers. And we want to, again, turn words into numbers using the distributional hypothesis. Our goal is to create a matrix where each cell contains the number of times the two words occur in the same sentence. So like in this table, how many times the words computer and technology appear together? They appear together 5 times in this hypothetical data set that we're looking at. And each row of the matrix is a vector, a list of numbers that will represent that word. So here at the bottom row represents the word baby, and those numbers are now going to be our representation, the vector for that word. What can we do with those numbers? Once we have vectors, we can plot the words in a graph. We can think about each of those numbers as a dimension in space. So if we had just 2 numbers, it would be 2-dimensional. Usually there are many more than 2 dimensions, but then we can measure, once we can plot these words in space, as I've shown in this little 2D plot, then we can measure distances and relationships between the words. And then for whole documents, not single words, but whole documents, we can average all those word vectors to get a single vector for the document. And now we can measure distances and relationships between documents. This is why we want to get to vectors and numbers from the words. What do we do with all those word counts? Or where do we get all those word counts? These models take advantage of big data sets and pre-training on a large data set and applying that model to smaller tasks later. So these really big data sets can include things like Wikipedia, Reddit, books, medical notes, and scientific publications, lots of other internet data as well. And there are many different ways to create those word vectors. I've shown you one way where we just create a matrix of word counts, but there are different algorithms that help us get to that same place. The end result is the same, where each word is represented by a vector, but there are different ways to get there. They also start in the same place, usually, with the co-occurrence counts. So there's an algorithm called latent semantic analysis from 1988 that uses word counts in a similar way to what we just saw. In 2013, a very popular algorithm called word2vec was introduced, which used a neural method to discover those vectors, and there are many other algorithms as well. More recently, there are also things called contextualized vectors. So word2vec and similar methods produce static vectors, where each word is represented by one vector, whereas newer methods create a new vector every time a word is used in a data set. These are contextualized vectors and are supposed to represent a word's meaning in context. So that helps with problems like some words have multiple meanings that change depending on where they're used. These are some of the methods enabling new tools like large language models. So just to visualize that last slide, word vectors traditionally are 1 point per vocabulary item. So here on this 2D plot, we have 1 point, one vector representing nature, 1 point representing science, 1 for religion, and 1 for art. With these newer contextualized vectors, there's 1 point or 1 vector representing each instance of a word in context. And so now we can see how, for example, the word nature or science or religion or art is used differently in different contexts. So you can see at the bottom of the slide, there are kind of 2 big clusters for the word art, representing when art is used to talk about, sculptures and paintings versus art as a verb, thou art to me a fly. I think this was a poetry data set that we used. Moving now from the vectors to the language models. What do we mean by the word language model? A language model is a model that assigns a probability to a sequence of words. Given a sequence of words, can we predict the next sequence of words? And we rely on some text data set, like those giant data sets I was talking about before, to estimate those probabilities. A very simple language model would be something like this. So what is the probability if we see the phrase to be or not to be, oops, that should say what is the, but maybe this is a good example. So to be or not to be, that is the, and you're trying to predict what is the next word. And so because I have this typo in there, that might actually, lower the probability of the word question because it doesn't match the very commonly quoted phrase to be or not to be, that is, what is the question? That is the question. That is the question. It's correct. So we would expect the probability to be high. And we can do that for unigrams, so counting how many times question follows the in our data set, bigrams, so grouping pairs of words together, or trigrams, so 3 words at a time. What are large language models? So what I've just described is the traditional view of a language model. What are large language models? These are also referred to as pre-trained models or sometimes as foundation models. These models rely on vast amounts of pre-training data. So not just Wikipedia, but Wikipedia plus everything else that you can throw into it. While some performance gains come from the model architecture, a lot is just coming from the sheer amount of pre-training data. Common pre-training sources, again, include web scrapes, scientific publications, books, and some examples of these large language models are things like ChatGPT, Claude, BERT, a slightly older large language model, Galactica, or Bloom. But these new models, like ChatGPT, aren't just language models. Some of you might have gone to a tutorial yesterday on reinforcement learning from human feedback, or RLHF. So after the model, that language model is trained, there's an additional step or multiple additional steps that encourage the model to produce output that looks good to humans. Briefly, that process looks like this. So we train the language model using the word counts to predict the next word based on the words we've seen. Then we generate text from the model and ask people to compare pairs of those texts, choosing the better text. And then we update the model using that feedback. So that's RLHF, which is an extra step on top of the language model. Now we're going to talk about transformers, which are the architecture under these models.
Hi, what a great audience. I'm David Minot from Cornell. Before I start, were there any comments from the internet?
This is more than a comment. This is something that they said that something changed in the code now, and it prohibits questions about specific people. And I don't know what they specifically mean by specific people, but I'm assuming that they posed questions that were centered around a particular community. And ChatGPT sort of responded with the response that, oh, I'm not capable of answering these questions, or something to that effect. And similar sort of prompts about, someone asked about being pregnant and over 40 and how to ensure healthy pregnancy, and it just gave generic health advice and said, go to the doctor for genetic testing. And that is sort of a problem, is what they feel. And the first question that produced a long winding answer included things that are sort of relevant to pain management strategies and things. This is just about the prior thing that we were discussing. Thank you.
No, those are great observations. I think I won't speculate about that. A lot of companies had the capability to do something like ChatGPT, but didn't. So OpenAI did. So we want to talk a bit about the details of the transformer architecture. This is sort of the type of language model that has become dominant in the field of natural language processing. One other thing I want to mention. So there was a question about asking about specific people. And I guess it's refusing to say things about people, but someone asked me the other day if I had written a particular paper with a colleague at Stanford, which I don't think we actually wrote. So that is a different way of asking about a specific person, suggesting that they've written papers. So, my vision of reinforcement learning with human feedback is sort of the fence in the desert with nothing to the left or the right. Like, yeah, there's a specific thing that it can't do, but there's a lot of ways around it. So for the specific transformer architecture, there's a few key terms that you might have heard tossed around. The architecture itself is surprisingly simple. It's just sort of the same thing repeated many times. The basic unit is what's called a perceptron or a classifier, where, as we said, a vector is a list of numbers. So our perceptron is something that takes a vector as an input and produces a 0 or 1 as an output. So you can think of this as a classifier that takes a specific set of numbers as an input. If you think of a perceptron as something that takes a vector and produces a single number, you could repeat that many times and have a number of perceptrons that are all looking at the same input, but producing different outputs. So that would look like a vector of numbers. You can think of that, therefore, as what's called a layer. So you have one vector of inputs, you have a number of perceptrons that all look at that same input and produce a vector of outputs, one number per perceptron, and therefore you're starting with a vector and ending with a vector, which means recursively you can just stack those on top of each other. A transformer is a particular category of multi-layer architecture that uses these layers to create iteratively refined representations of individual tokens. So we'll go into that in more detail. The thing that's particularly interesting and what made the transformer architecture really work beyond many other neural network architectures that were similar is this idea of attention, that certain words pay attention to other words more than other words do. And that notion that you can sort of construct the graph of connectivity in a sort of soft way between words as you go on, and you can learn how words connect to each other, that is what the attention mechanism is for, and that's what really, along with massive compute and giant data sets, made something like ChatGPT possible. Okay, so there are a lot of ways of showing the transformer architecture. You've probably seen these diagrams. They've sort of coalesced on one that I'll show you a little later, but the basic idea of the transformer architecture is that we're going to deal with all of the words in an utterance in parallel. So it seemed sort of natural because we think of a sentence, we process a sentence in sequence. A lot of the earlier methods for processing language dealt with sequences of neural networks, such that the output of the encoder for a particular word would then be fed into the system for the next word. This is called a recurrent neural network. The reason that doesn't work that well is because it's very hard to transfer information from one word to a word that's further away. And it's also not very efficient because you have to wait for the output of one word to start working on the output for the next word. So what the transformer architecture did is it works on every single word in the context at the same time. And the way that words sort of talk to each other and provide information to each other is through this attention mechanism, which happens over multiple repeated layers. I like to think of the layers as sort of what in the 2000s and 2010s we called iterations. But it sort of works better with the hardware to build this out as a fixed number of layers. Okay? So the key point here is that the transformer architecture is very well adapted for the specific high-performance compute environment that is available today. So if you think, like, why is NVIDIA stock going up? It's because it's very good at this particular architecture. Okay, so the way that a transformer works, we start with input embeddings, self-attention, feed-forward layers, and encoders and decoders. I just want to list these phrases so you know to look for them as we go through the next two slides. The idea of input embeddings is basically the same as that type of word embedding that Maria was talking about earlier. So for every distinct string that you agree to recognize, you have a particular vector. So the string art has one vector regardless of whether it's a noun or a verb. So that's where we start. So when you initialize the model, every string that you recognize as a token gets that embedding put in to its position. And what we're going to do is iteratively refine the vector for each word so that it goes in different directions, and we get the contextual representation of the word in its position. The way that self-attention works, the intuition here is if I say the, and then you think, what's the next word in English? It would be different in French. It's much more likely to be a noun than if you didn't know that the word in front of it was the. It could be an adjective, could be something else. But that word, that's the immediate previous word tells you something about what the next word is going to be. Similar with the word after a word. So if I say blank ate, again in English, then that's probably some kind of entity that is capable of eating. So you know a lot more about that word that appears in that blank than you did before. So that's the idea of why do words sort of need to talk to each other? Because especially words that are nearby provide a lot of information about the contextual meaning of a word. There's also the more generic topical or thematic information. So this might be a longer context. If you see words like fact, conference, and attendee, then you might not see a direct sort of grammatical relationship with a word that's 20 or 100 or 1,000 tokens away, but it has a semantic shift. Like those words tell you something about what the context is. So the attention mechanism is really about deciding which words should provide information to which other words. Finally, there's an aspect of feed-forward layers. This is a bit more esoteric, but you can think of it as sort of the model tends to use these parts of the network to kind of encode prototypes. And then as you build up a representation, that representation sort of picks out one of those prototypes to be the representation for the next layer. Sorry, that's a little bit hand-wavy, literally hand-wavy. But that's a large part of the model that is providing a lot of the information. It's been shown that those can become much more interpretable sort of in the later layers, but in the middle, they're a bit more difficult to look at. Okay, so another set of terms that you might have heard is encoder and decoder. The difference here is that an encoder is going to take text and it's going to produce vector representations of the tokens in that text. A decoder is a system that will take text and produce a probability distribution over what the next word is. So one of the implications of that is that an encoder might look at an entire sequence of maybe 1,000 to more tokens, and every word is going to be able to look at every other word. With a decoder, where you're producing a new sequence, you can only look at the words that have already been produced. So it will mask out all of the words that it has not seen so far. Okay? An encoder-decoder, for example, the T5 architecture, has both an encoder part and a decoder part, where you could think of the prompt that you give it as something that would be put into the encoder, and then the continuation that you get back would be the part that comes from the decoder. Okay. So, for example, if you have an encoder-decoder, you might have 6 repeated layers. 6 is sort of a very small model, which would encode the input that you give it, and then 6 identical output layers that would decode a response that the model would produce. Okay? And that's where we get this, I think it looks like a chemical plant, a fractional distillation stack. If you look at, is this mouse working? Okay. So you can read this off now. You put the input, you look up the embeddings for each of the words that you identified. We'll show you more about that in the tutorial. And then for each layer, that's what this gray box means with n times, you would generate your multi-head attentions. So this is for the current layer, which words should look at which other words. And then once you've gathered the information from those other words that you're paying attention to, you would hit that feed-forward layer with the representation that you have, and then generate the representation of the word token for the next layer. So that's the complete loop. That's all there is. It's just matrix multiplication. Okay. And then in this case, we would take the outputs, which you're generating one word at a time. You would do a masked multi-head attention, so you would only look at the outputs that you've already produced. Take all of the information from the embeddings of the input, and then do the same process, but actually produce a probability distribution over the potential next token. Okay. I've given you a lot of information. Questions? Yeah.
Hi, I have a question about the property of reproducibility.
Yeah.
Maybe both on like, can you train these in a reproducible way? And then on like the output side, is it possible to, given the same question, get the same result back?
Yeah, okay. So there's 2 similar questions, but they have different answers. For the input training, it does matter. So we'll talk more about training and pre-training. The model will be trained on a gigantic set of documents. And when the model is sort of initialized, the documents that it sees at that point will have a bigger effect because it's not as good of a model, and so the gradients are going to be larger, and it's going to be taking larger steps. If it's already seen 1 billion documents, it's probably pretty good, so it's not going to be taking as big steps. So the order in which the model sees different documents does actually matter. A lot of these things also happen in parallel distributed situations, and it's very hard to keep things consistent if you've got like a giant data center worth of GPUs or TPUs running. So doing things consistently is a big challenge. The other question is, can you get the same output? So you probably noticed a lot of you might have put the same question into the GPT prompt, and you might have gotten different answers each time. So let's think about how we generate an output. The input, it's always going to be broken up in the same way. It's always going to get the same input embeddings. And there's nothing in that encoding step that is not deterministic. You will always get the same result from that. The output, however, is producing a probability distribution over the next word. And then it's sampling from that probability distribution. That's actually really important. If you just pick the most likely word, then have you ever done that thing with predictive texting where you just tap the word that's most likely? Like, what does it look like? It's sort of very anodyne. It might sort of repeat itself. If you just take the maximum likelihood word at each case, you will get the maximum likelihood sentence, which is almost certainly not interesting. Like, a lot of the words that we use in everyday language are quite rare. And so it's really important, actually, to generate realistic text to be picking sort of down the list. So there is a stochastic element to the text generation, which is why you get, Melanie was looking at, I forget what the question was, but you were asking it multiple times, and she was always getting 4 bullet points, but the bullet points were different. Like they were sometimes in different orders. It wasn't consistent. And so computers cannot actually have randomness. There is sort of a random seed that goes in there. And if you give it the same random seed with the same inputs, it will give you the same output. But that's not something that's, I believe, exposed by the GPT API. Do we know that? Okay. Luca's saying no. We don't know, or it's not possible? Okay. Yeah. Can you wait for the microphone?
Thank you. I have a question that you might be answering later on, but it's intriguing. So if you wanted to poison a model, how would you go about doing it at this early stage? Or it must change through the stages, right? Mm-hmm. And what levels of poisoning occurs at what stage? Thank you.
Yeah, so there's model training, which is where I would poison it. And then this process itself, I think, is fairly deterministic. Like there's not a lot that can go wrong or right here. At the point where you've got the model and you're generating from it, it would be hard for me to see how you could direct it too much.
So the follow-up here is, if you were an actor and you wanted to take a completed model or a model that is well-trained already, such as, for example, GPT-4, mm-hmm. and you wanted to create, you really wanted to lay down some misinformation for the model to, uptake. Mm-hmm. This would be like a drop in the ocean at that point, correct? You would have to create a profound amount of data. Is this a correct assumption?
No, I think it would be fairly easy. Think of the volume of data that's needed to make ChatGPT have its sort of apologetic, unwilling to offend facade. It's on the order of like, do we know what the typical RLHF training set? Sorry? Like 10K. Like, can you produce 10K examples that are fitting with your agenda? Good. That's all you need. And a bunch of commute, but not that much. Yeah, I'm very certain that by the end of the summer we will see language models that have political biases, like explicit political biases. Yeah.
Oh, I had a question around like going through this process that was really illuminating, but I was curious if you could talk about the time or that it takes to train these models, or like now that, let's say, ChatGPT-3 or like GPT-4 exists, is it much faster to retrain them? Is there like efficiencies?
I might defer to Luca on that, but there will be a point in a few slides where it'll be easier to talk about that. Okay, all right, we'll move on. We wanted you to hear because we knew you'd have lots of questions. So let's just go through an example. If I have an input sentence, my encoder, I might look up my embeddings. They would be the same for every instance of a given token. Then I would run through this encoding process multiple times, and what I would get out would be a vector for each word or a vector for the document. Okay? If I had a decoder, I might do something very similar, but rather than getting a vector, I would produce a probability distribution over continuations. Okay? So how can we use language models? And I mean we, the people in this room. So one thing that could be interesting, a lot of people have this idea that ChatGPT, for example, is sort of like a search engine. I think that idea took a lot of people in the natural language processing by surprise, because that is not how we think about it at all. But it kind of, in retrospect, looks like something that should give you search results. For something more like fact, we might actually want to use a model to probe biases. We might want to use a model specifically to probe the biases of a particular collection or of the pre-training collection that was used for the model. There was sort of this moment with word embeddings about 8 to 10 years ago where natural language processing people sort of looked at the models and realized, wait, these models encode biases. We have to fix this. This is a bug. And all the social scientists and researchers said, you have a model that can measure biases? This is great. We can finally actually get information about this. We can say something quantitative about bias in data sets. So I think that the people in this room have a lot to bring to this conversation and have different perspectives that can be very refreshing. But in general, the pattern that you will see is something called transfer learning. So the traditional view of machine learning is if you want the system to do something, you provide a bunch of examples of doing that thing and you train it. Transfer learning is the idea that you would start by learning to do something else and then use the result of that something else to start training the thing that you specifically want to do. It took a long time. People thought this was a good idea long before it actually worked. The idea that has become dominant is that you would pre-train. So this is you are training, but you were training without a particular specific objective that people care about on something like predicting the missing word using lots and lots of data. And then you would fine-tune or prompt a model to do a specific thing that you care about. Okay? A view that I have of transfer learning is that pre-training is sort of about building a general purpose engine, and then fine-tuning or prompting is about putting a specific task head on that engine that will then do the thing that you actually want to do. So for example, if you were classifying text, you want an output that is 0 or 1, and therefore that would produce that 0 or 1 output rather than predicting missing words. A lot of other tasks, you might want to have sort of a text generation output. And so this is kind of the view that we have of the modes, and this is where I'm going to get to that computation question. So pre-training is usually done on a very large collection of data, usually as much as people can get. It's done with a very large amount of computation, usually sort of data center scale computation. And it produces this model. So think of this as like a file that is a gigabyte or so on disk, maybe up to several hundred gigabytes. The idea of fine-tuning is that you will take a much smaller amount of additional data, change the model, and rewrite a new copy of that entire model that does the specific thing that you want to do. For example, this is, we're trying to identify an image of the Roosevelt Island tram. I can then take my new model that I've written to disk and ask, is this image an image of the Roosevelt Island tram? And it can tell me yes or no. So that is the best way to do a particular task, but it's a lot of work. So it's much less work than pre-training, but it's still, you have to create a new file. You can't do this through an API because you need to produce a new model that you then have to serve. So one way that a lot of people are very excited about working right now is take the pre-trained model and use it for specific tasks. And so one way to do that is called few-shot learning. This is an example of in-context learning because you are not changing the model, you're only changing the context that you're giving it. The idea of few-shot is you give a few examples of the thing that you want or the task that you want to do, and then you hope that the model that has been pre-trained has some kind of latent representation that's useful for that task, and you're just sort of helping it identify that representation, and then you can ask it something new, and it will give you an example. The other alternative is what's called zero-shot or instruction-based modeling, where you don't give an example of the thing you want, you give a description of the thing that you want. People seem to really like this. This is kind of the way that people do. We'll give you some more examples of these. But to the question, so pre-training, that's like weeks on hardware that you can't afford. Fine-tuning, that could be as little as like 5 minutes on a free tier Colab notebook from Google. It could be a day or so on a beefy GPU. It's not particularly difficult, but it is non-trivial. We have a notebook that gives you an example of this. I don't know if we're going to be doing it in this session. Few-shot learning, you can do that from an API, so that's much less work, but it does require giving good examples and it doesn't always work. And again, zero-shot, same thing, much less computation. Okay.
Hi, everyone. I'm Melanie Walsh. Okay, so we promised that this was going to be a hands-on tutorial, so let's actually get down to business. How do we actually use these large language models? So the most common way that people work with large language models in a practical sense is with the Hugging Face Python library. So I'm just curious, by a show of hands, how many people are familiar with Python, just so I know who I'm speaking to? Okay, so lots of people are familiar with Python. If you're not, that's okay, but we're going to be focusing on Python for this particular tutorial. So yeah, Hugging Face is a machine learning application company. They've got this great Python library that makes it pretty easy to load a model and to do a lot of the hard stuff that you need to do to use a model on your data. And they've got models including T5 and GPT-2, a lot of the open source models that you might be interested in. Additionally, they have a lot of documentation, which is really helpful, that helps people understand how to use the models. And they've got a very vibrant community, many active users, and that makes it, a lot easier for you because if you've got questions, there's a lot of help. But unfortunately, even though there's a lot of documentation, oftentimes this documentation is geared toward people who know a lot about deep learning or know a lot about NLP. So if you're not one of those people, it can actually be really difficult to understand the documentation, and that's where this AI for Humanists project, where we've been trying to make an intervention to help sort of translate this documentation to other kinds of users. So when you're thinking about using a large language model, you might, you're going to need to actually pick a model at some point, and it can be kind of difficult to know which one might be best. So there are lots of models available on Hugging Face, including models that exist beyond English. And so if you're looking for a model, we recommend browsing through the collection, reading papers that might be relevant for your work. They also have a number of leaderboards that represent how the models perform on different tasks. So that can be helpful for identifying a model that might be appropriate for your work or what you're interested in. But again, these leaderboards are really focused kind of like internally on the machine learning community and the NLP community. So they're very focused on particular tasks and state of the art. And we might not care about that. So that's another thing to think about. Okay, so can you actually work with large language models on your laptops right now? And the answer is yes, but with some caveats and modifications. So like David was saying, you may have heard that NVIDIA, the stock is way up because people really care about GPUs, because we need GPUs to work with large language models because of that parallel processing that David was talking about. Unfortunately, most laptops don't come with GPUs out of the box. Maybe you have some gamer friends, people who are really into video games. They often have computers with GPUs, but most computers do not. However, Google Colab offers free access to GPUs, and if you pay for access, you can also get paid access to even more GPUs, which is really helpful. There's going to be one part of the code that I walk through in a moment where you're going to have to specifically send what we're doing to CUDA. CUDA is the parallel computing platform by NVIDIA, and so to actually take advantage of the GPUs from Colab, you're going to actually have to include this line of code, and I'll flag that in a moment. There's also going to be some pre-processing work that you're going to have to do with we're focused on, again, textual data in this particular tutorial. There is some pre-processing work that needs to be done for your text if you want to use a model on your text. But luckily, again, with Hugging Face, a lot of this is taken care of for you. But just to explain kind of what's going on here, oftentimes there's going to be some tokenization that happens. But it's not only splitting text up into words, but often it's actually word pieces. And then there are going to be some other special tokens that are included so the model kind of understands how specific sequences are supposed to be processed. So for example, these are some of the special tokens with BERT, and here's an example of a Wordsworth poem, and this is how it looks tokenized to be prepared to be run in a BERT model. And this is important just because this is going to come up in the notebook that I'm about to walk through, and you can see that individual words are being split up into word pieces, and we can talk more about that maybe in the Q&A. The other thing that I wanted to talk about just quickly, because this is going to come up in the notebook, is that in this text collection that we're about to work with, we're going to have words, obviously, so in this particular sentence, the art of science, and each of those words is going to have a particular ID, so we can keep track of the same word that's coming up in different places, and it's also going to have a position, because we want to know this word is showing up in this particular position, this same word is showing up in a different position, and then we have a vector representation for each of those positions. And this is what enables us to understand those words in context, which again is like one of the big affordances of large language models and one of the differences from the methods that have come before. So we are going to focus not actually on fine-tuning, so I'm just going to say something really quickly about fine-tuning. We are just going to be using a pre-trained model for this particular notebook that I'm about to show. So again, all of the work has already been done, so there's going to be no modifications, and we're just going to apply it to a new text data set. But if you wanted to, like David was saying, we could fine-tune this model, and you can, sometimes it would only take 5 minutes, sometimes it can take longer, but you can make it better suited for your particular data set, your particular task. And yeah, you can set it up to do something like a labeled classification task. We have a Colab notebook up on our BERTforHumanists.org website. We've rebranded to AI for Humanists, but we haven't updated the URL yet. But we have a Colab notebook that demonstrates how you could use a large language model to classify Goodreads reviews based on their genre. So that's something that you could do. But for now, I want to show how we can use a pre-trained model to do some work with a particular text data set. So if you click on that bit.ly link, that is bit.ly/fact LLMs1, it's going to open up this Colab notebook. So in the main thing that we want to accomplish with this notebook and this example is to help you get an intuition for how a large language model works, specifically with what I was talking about representing words in context. So the text data set that we're using here is a collection of Sephora makeup reviews. Connie Yi, who I think maybe works at Google now, as an undergraduate student, collected these makeup reviews and did a hilarious project about all reviews that mentioned crying or sobbing. These are more than just reviews about crying and sobbing that we're about to look at, but this is an example of, data on social media, data on the internet that we might be interested in exploring and studying. So one quick note, if you want to edit this notebook for yourself, you're going to probably want to save a copy in Drive and maybe put your own name on that so you can run and edit this notebook. But what we're going to be working toward is something like this. So this is kind of the end goal. So what this plot shows is every single time the word sensitive shows up in this collection of 5,000 makeup reviews, and if you hover over each point, you can see the context in which the word sensitive has come up. So here it says, I have sensitive acne-prone skin, sensitive skin, I have combination sensitive skin. This whole cluster is representing the word sensitive in relationship to skin, and if you go down over here, you can see my sensitive eyes. I'm someone with super sensitive eyes. I've got sensitive eyes, and you can see that the word in a different context is showing up in a kind of different cluster. So again, this is kind of one of the big affordances, and it allows us to look at how the same word is being used in different contexts, and also to compare representations of different words. So that's what we're working toward. So if you want to run the whole notebook, you could go up to runtime and you could run all, so you can start to play with it when we get to some of the more exploratory parts at the end. But I'm not actually going to run the code, but I will just briefly talk through what's happening here. So the first thing we're going to do is we're going to install the transformers library. This is the Python library from Hugging Face. And then we are going to load the tokenizer that we need for our large language model, as well as the package or the module that we need for our model. And then we're also importing some other things that we're just using for this notebook, pandas for working with data, scikit, the scikit-learn library for doing some PCA that I'll talk about later, and a data visualization library. But none of this is necessary. This is just all extra stuff that we're going to do to explore the data. And then we have some other libraries. So the first thing that you're going to need to do is load your text data set. And so it doesn't really matter how you do this. However you're comfortable with loading text and getting it into a list of texts is completely fine. So we're loading our data set in those couple of chunks of code, and then you can see that our data set looks something like this. We've got the number of stars for the review, we've got the text of the review, we've got a title, the brand, the name of the makeup, and a URL. So just to give you an overview, these are mostly mascara, eyeliner, and primer, just so we can understand the results a little bit later, and these are some of the brands that are represented. But again, the main thing is just getting this list of texts, and so if we look at a particular item in this list, here's one text, I finally caved, trying this after reading so many great reviews, yada, 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 conclusion, this mascara is not so sexy. Okay, so once we have our list of texts, we're going to load our model. So we're using that auto tokenizer, and the model that we're loading is something that we found from one of those leaderboards. This is a model that's really good for sentences in particular. And, this is the tokenizer. So like I said before, the main thing that we need to care about when we're pre-processing our text is that the tokenizer matches the model that we're using. So we're loading the tokenizer, and then we're tokenizing the text here, so we're feeding in our text to the tokenizer, and you can see that same particular review, here's what it looks like when it's tokenized. So it's being, some words are being split up into word pieces, etc. And then we're going to load the model, and you can see here, this is the part where we're sending it to CUDA so we can take advantage of that GPU. So now we've got the model and the tokenized text, and now we can get to work. So what we're doing here is and we've commented out most of this code so you can, after the fact, dive deep into this and try to explore it even more and really understand what's going on. But basically, we're just pulling out, for every review, every single word, we're pulling out its vector representation so we can get that rich representation of the word and its word ID, and we're just making sure that those line up. And then in this part of the code, we're just mashing all of that together for all of the reviews, and we're normalizing all of the vectors. And then in the next couple of sections, we are just creating some functions and some ways of first taking a word and finding all of those word positions that I talked about. So we're able to look for the word sensitive and find every single position in which it has showed up in the collection. And then we're just going to create some other little helpful functions and ways to then go from a word ID or a word position back into a word. So then we can see, for example, that each of these IDs actually correspond to the word sensitive, which could enable us then to start getting the words in context. So this particular word position is showing up in this specific context, good for my sensitive eyes, lots of people with sensitive eyes in this data set. Okay, so then we have some other just little helper functions for actually getting that context, so asking for a word, getting the context, and then cleaning up and displaying it. This is a lot of basically just work for creating a nicer display so we can get the word bolded. I don't know if you can see that. Maybe I could zoom in for each of the words. Okay. So then what we're going to do is we are going to take the word vectors. There are many dimensions for these vectors, and we want to be able to plot them and compare them in 2 dimensions. So we're going to use PCA to reduce those all those dimensions to just the 2 dimensions that capture the most variation. And that's going to allow us to have something like this. So each time the word sensitive appears, the context, and then a way that we can plot it on XY coordinates. And then we have some more helpful functions for actually taking the text and matching it with the metadata and the original context so we can actually understand the collection a little bit better. And then we're importing this data visualization library. And then again, we can have that word sensitive and find all of the different use cases. Like I said, here's sensitive skin down here. Sensitive eyes are over here. Out here, we've got not for the sensitive type. I'm super sensitive, so other uses of the word sensitive. So once you have that, you can search for all different kinds of words that show up in this collection and see how they compare to one another, how they're being used. And it also helps us understand, again, this is the pre-trained model, so it has not been fine-tuned on this data set. So it gives us some intuition for how these words are being represented in the model itself. Because of the interest in crying and sobbing and like how makeup holds up in water, we were searching for the words pool, gym, wedding, funeral, office, and party. So you can see up here, these are all wedding words. Used it during my cousin's wedding. My sister bought it for her wedding. These are the words party. I did makeup for a bridal party, so you can see bridal party is kind of close to this wedding cluster. So there's kind of a lot of fun stuff that you can explore within these representations. And if you run the whole notebook, you can put in your own keywords to explore what you want to explore. When I had my students working with this notebook, one of the first things that they were really interested in was looking for racial and ethnic terms. And actually in this particular data set, There aren't a ton of racial or ethnic terms, so I think my students were looking for like white, black, and Asian. White and black are mostly referring to colors in this particular data set of reviews and not as being used as racial terms, although the word Asian actually is used a lot in this context, and I thought that was really interesting. So again, basically this is just showing how you actually get these rich representations of words for, using a large language model on a particular text collection and giving you some intuition for how you can start to look at those words and think about them in a slightly more practical sense. So yeah, if you run that notebook, then you can start to explore for yourself. But yeah, I think that's what we have before moving on. I think we're not going to take a break in the interest of time.
I am so sorry to take away your break, but I'm going to talk a little bit about prompting. My name is Luca. Nice to meet you all. Let's get started. So as David and Melanie described, there is this sort of categorization that you can follow for which kind of patterns people follow when using a language model. You can fine-tune it for a task, the model's you pre-training, then you fine-tune it. And then at the bottom, David was talking about these two modes of using a model, either in this few shot setting where you provide a couple of examples and see if I can follow along, or even zero shot. Maybe the model somehow can do the task that you want to do without doing any specific extra training to this task. These last two is the two modes that are primarily used when people talk about prompting models. You're really relying on the fact that these models somehow have obtained ability to perform certain tasks if you provide them with a little bit of information or no information at all. So these are two simple examples of how you might do that. You might have a little instruction that says reverse the letters in the word. You provide that word, the parts in gray is the part that you type, and then the model will fill in the part that is ... Or perhaps you have to show the models a few examples, how to do that. You provide, again, the instructions, and then you provide a couple of examples in these cases of reverting, and maybe by the third time, this large language model is able to perform this task. As these models have been trained on more data, are larger than previous models, maybe have been fine-tuned or use reinforcement learning to better adapt to these use cases, you can start really customizing and going using more complex instruction. And I will show an example in a second. But things that you might do is you might include examples of the output you want. Might include explanation of what you're trying to do. You might include in your prompt the format that you want the model to return. Maybe you want JSON, maybe you want a bullet list, or things like that. You can request the model to output for an explanation. These are not, there's no guarantee that this is an explanation, but there is some work that shows that this leads to more faithful interpretation of your commands. And also you can add your own personality or request for certain values to be expressed in the output of the model. As you saw during the first few minutes when we play with the model will inject what the value of the people who created it are, regardless of what you ask it to do. But to some extent, you can also customize a little bit the output. So you go from these very specific things, and I'm just putting an example of a prompt that I was using a few days ago to analyze a corpus of scientific literature. So in this case, I was trying to use a model to process a corpus of papers, and I wanted to extract references from papers in a very standardized format. And so I was able to provide the model with a little bit of context. I give it the paragraph, the title of the paper, I spend way too much time coming up with somewhat reliable instructions to help me do this. I provide a few examples on the format, and then I run the model. Hopefully I get some usable output. It's very convenient as a mean to, if you want to analyze a corpus for specific properties or to get a better understanding. These models offer a lot of flexibility in terms of like what kind of operations you can do. Not capturing this is the fact that it's quite brittle. So this was a lot of operation. You have to come up, also not capture the fact that I have a set of parallel pipeline to verify that the output somewhat makes sense, and I have controls, and then I can have some human annotations verified, but it enables some datasets analysis that is perhaps convenient for the research you are conducting. To the last point, one thing to really keep in mind that really drives me nuts is as you provide more instructions, this feels like you're writing a program, right? And the program has this idea of like perfect execution, but these models are not programs. A prompt is not a structured query or a program that you're executing. So you have a lot of flexibility in what you request. You have to write no code. There is no specific syntax that you have to follow. But it's really hard to predict sometimes what's going on in the output, and very tiny changes. You know, you change a preposition in your prompt, it might change the output dramatically. So play with them with care, I guess. I'm gonna skip this part because we don't have time. And what I wanna talk about is I put together a little demo that I'm gonna reload from here so I can get the latest version. This demo that I put together, I'm going to go through, shows you two different ways you can prompt a large language model. Method number one is by calling APIs from a private company, your Anthropic, your OpenAI. I'm not going to use their official library. I'm going to use a third-party library that makes it really easy to compare multiple models. Which might be very useful if you're doing fairness research and you want to compare how different company treats the same prompt. And then in the second part, I'm going to show just a couple of instructions on how, if you want to run a model locally, so this is one of the open source models that are available online. There are now libraries that make it very easy to use them. And so I just want to give you a flavor of how that looks like. So for the first part, we're going to use this library here, called LLMs. This is a third party. It's not an official OpenAI or Anthropic product. I like it, but I'm not endorsing it as like a perfect solution, but it works really well. Yes. It's on the slides, but I will. Oh, no problem. So it's bit.ly fact dash LLMs 2. I'm going to leave it here for 3 seconds. 1, 2, 3. OK. OK, cool. So yes, we're going to use this library called PyLLMs. You can install it from pip. It installs on a notebook. Doesn't require any special things. And first thing I have to do to use it is all these companies usually require you to provide an API key when you make a request. And in this case, I have this API key saved in a file in my Google Drive, but you can also copy, paste it, and put it here as well. I'm going to show OpenAI and Anthropic, and I'm going to show how you can use both at the same time. So after you import the library, you can just get a model endpoint. So I'm just going to start here with the GPT 3.5 Turbo, which is the closest thing OpenAI has to ChatGPT that you can call through the API. It's not the same model, but it's really close. And you can use it as if you were using the the web UI. It has a couple couple advantages over the web UI. The biggest one is that you can save the responses you're getting, so you're not forced to like screenshot, copy, paste. You can go back, re-examine what was given to you, and so on. So in this case, I gave it a text input. I pass it to this complete function, and I get an output. The output to the prompt, who are you? In this case is, I am an AI language model created by OpenAI, blah, 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 blah. It's the standard one. You all know it. Another nice thing about this library is that it returns you helpful information alongside the text. So it will return you what model you use. Most importantly, it will return you the cost in US dollars. OpenAI has a very opaque dashboard where you track the cost. It's very easy to go over. Having nice library that help you keep track are a nice plus. So in this case, to generate this text was about 0.08 cents. Another thing you can do is you can simulate conversation that a user would have with the system. So let's do that next. I'm going to create a little history list where I'm going to keep adding a conversation, and I'm going to populate in the next few cells. So things that you can do, you can provide, and the thing that I should say is when you interact with some of these private APIs, in this case OpenAI, there are roles that you can assign to a conversation chat. So you can say this came from the user, this came from the system. You can inject text that was generated by the system. So you can pretend to be both the user and the model responding to you and see how, after a few turns of conversation, how the model progresses that conversation. So in this case, I'm giving it some base instructions. This is something that people usually, for some application helps giving some baseline instructions to the model. So in this case, I'm telling the model, you are an AI assistant, you know which day it is, the location of the person you're chatting with, and I'm passing this information in. I'm giving today's date and the location. And I'm adding this first to the conversation history. Now I'm simulating a user, asking, who are you? And then I'm simulating the system. And you can see in this case, I'm inserting a text from the system that is different from what we got in the earlier cell. I'm just saying I'm an AI language model, but I'm adding this part that says we are a tutorial at fact. So I'm playing as if I were the system. And then subsequent, I asked the model another question in the chat. Now I'm asking where is fact happening? And the model has picked up the, because I gave it the date and I said that we are at a fact conference. Now the model can respond, fact stands for Conference on Fairness, Accountability and Transparency. The conference is held annually at different locations. In 2023, the conference is in Chicago. This is using the previous information that I gave the model to do a little bit of inference and, in this case, make a correct inference given my request. You can also do things when you're making a request to a model. You can ask it to have the output in a specific format. So if you ask it, be as brief as possible. Now you get just fact is happening in Chicago, Illinois. Now I think to be careful is depending on where and how you inject this information, the model goes completely off the rail. So in this case, I'm adding your response has to be as brief as possible to the initial message in the conversation. And now when I ask the model again, where is fact happening, it's telling me that 2022 fact was in Chicago, Illinois. And this was a very small modification to the input that had a pretty big change on the output. So yeah, it's useful to be just very careful and vigilant when using these models. Unless you're studying when this kind of phenomenon happen, and then in that case, it's an interesting finding. Using this library, another thing that you can do is you can call two models at the same time in case you want to see how they respond differently. to the same request. In this case, I'm using Claude by Anthropic and GPT-3 Turbo again from OpenAI. I'm changing the request a little bit. In this case, it says, write me a program to greet a user. Make sure to refer to the user. There's the repetition here, but to refer to the user using their chosen pronouns. This one is a very fun prompt because it really shows the limited understanding that the model has in terms of like really interpreting what the request is. So in this case, for example, the Claude model says, here's a Python program that very correctly, asks for the pronouns. Of course, only 3 pronouns exist here. No need for anything else. And then it returns this nonsensical response that is, hello, how are you doing pronoun today? We'll replace it, but it will say, how are you doing she today? Really nonsensical. But okay, let's see what GPT-3 did in this case. It says, I can't run code, not really relevant, but sure, thank you for letting us know. The program here, okay, asks for name again, asks for pronouns. In this case, it's able to handle cases where the pronoun is not she, he, or they, but again, it will respond, hello, name, how are you, how are they doing today? Really non-grammatical, but it tried, I guess. But anyway, this is a way you can compare the output of 2 different models, see what's going on. So this is, it's really handy to be able to use commercial API, and you can, like, in this way, and compare quickly, study the fairness issue that perhaps arise from this model and so on. But it's, there's, it's kind of sad if all the work that we do it's against commercial available API. It's good to know. It's good to have an opportunity to run models locally as well. So I'm going to show that one next. Now, a couple of things to keep in mind: pros and cons of local models. One thing that you can do with models that are available in the public is that often they come with the pre-training data that they were trained on. So I'm going to use this one called Falcon, and the pre-trained data used for it is available to the public. So you can really study the effect and the interplay between the data that we use for the model and the output of the model. And also they can run in a notebook, which is really nice. You don't have to have any special access or special budget. They can run on the free version of Colab. They can run on consumer level GPUs. That is really handy. The con is that they're sometimes really rough. They don't have the same steps in training that OpenAI or Anthropic have used. Usually they miss the reinforcement learning part. And so sometimes they go off the rail really quickly. They can generate very harmful content, content that is really disturbing, problematic, non-factual, and so on, even more than commercially available models. And also the tools themselves are a little bit rough. This is a rapidly evolving landscape, so the tools require maybe a little bit more expertise and so on. What I'm going to show in this notebook, I'm going to use a library called Falcon Tune. It showed up on GitHub 2 weeks ago. That's how rough things are. But it's really nice to use, and it can run a variety of models. And it uses a technique called LoRa. You don't have to figure out the details of this, but suffice to say is that it's an efficiency-oriented technique that makes these models much more easy to either fine-tune or run. And I'm going to use this specific model. So to use this one, it's really easy. You download the model, you install the repository, and then you are able to generate text using this command. Now, the interesting part is that when I ask, in this case, write a Python program to greet a user, it will spit a lot of content, but then this is all I get. So there's a different capabilities. Maybe this specific model is not great at coding, but it can be used to study at a task. And it's nice to have models available where you can study phenomena and asking questions that are not available when you only have black boxes, such as APIs. This is all I have. I'm going to hand it back to Maria.
Okay, in our final moments, we have another little Menti poll if you'd like to participate, just asking about what surprised you and what you learned, and if there are things we didn't cover that you still want to learn about. So if you have some energy left at the end of these 90 minutes before lunch, we'd love to hear from you, and I'll put the answers up on the screen after a few moments. You can use the QR code on your phone or go to menti.com and use this code. But we'd like to thank you all for coming today. We have some resources in the slides, some links to other courses and readings. There's so many resources online, and as Luca just mentioned, there are more and more all the time. These are some that we like. And from our perspective, there are a few takeaways that we hope we've communicated to you. So models are big and complicated, but they're made up of simple pieces that we can all approach. You don't have to be reliant on the interfaces that are given to you by companies. You can engage with many models directly, and we've shown you examples both from commercial examples where you needed API keys and you might need to pay for access, and models where you don't need to do that. And while it might be the case, depending on the domain that you're coming from and expertise, that other people might know more about the technical architectures, there's still so many open questions about these models that would benefit from your and everyone's perspective. We need a diverse group of people critiquing and engaging with these new technologies. So with that, I will just go back to this Menti poll and show what people are saying. Again, you can, if you still want to join menti.com, and that's the code at the top. And possibly we have a few minutes for questions. I'm not sure. I guess it's lunch after. We will hang out for a while afterward. And yeah, maybe we can take a few questions. Maybe if everyone wants to come up.
Hey, my name's Emily Hadley. I'm at RTI International. I thought you had a really great slide deck, and I saw you had some other slides on your website. And I think these are really useful for some of the stakeholders that we communicate with. What is your policy on like sharing your slide deck with other people in your collab notebooks and that type of thing?
Yeah, they're all open source, so feel free to share them or use them however you want. I think we have like a recommended citation on our website, and that's like all we ask for. But yeah, we would love if more people were using them and sharing them.
Hi, Chris Norville, University of Cambridge. First of all, thank you very much. I thought that was really interesting and I learned a lot. One thing I found really interesting when we were talking earlier in the session was about how the same question can result in different outputs because of the sort of stochastic nature, I think you said, of the models. I was wondering if you could talk a little bit about maybe how that works under the hood and what that might mean for being able to sort of probe into these models in a bit more detail and understand why one answer was given as opposed to another answer in any given scenario. Thank you.
So there are different levels how that plays. Some of them are can be controlled on and off. Some of them are software and can be turned off. Some of them are even hardware. In terms of probing, what folks would usually do is that instead of using just the actual output, they would look at the probabilities that are emitted by the model. The big, I guess, gotcha there is that commercial companies have stopped returning probabilities, or they're adding noise to their probabilities so that competitors cannot reproduce their work. That is unfortunate. That's why having access to local models is useful, because you can get access to those values. But otherwise, you have to repeat and sort of try to capture like the variance in the outputs that you get every time you ask the same input.
All right, thank you so much. We'll hang out for a little bit if there are any other one-on-one questions, but enjoy your lunch and the rest of FACT.